Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
His interest, his thesis, his really recent work. So take it away.
Can you hear me?
Yes.
Okay. I'm glad to be here, and I'll be talking on the topic of collaborative algorithms for a class of clustered wireless networks. This is going to be the outline of the talk. We're going to talk about wireless networks. So wireless networks invariably have to deal with some kind of protocol or the other. So throughout the talk, I'll be maintaining one particular protocol and proposing algorithms on that particular protocol. So we'll be looking at the protocol first, what that is. And then I'll give you some results on the protocol. We'll go into algorithms, what are all possible collaborative algorithms that you can propose on a wireless network. I'll give you 4 of those. You can propose a lot more, but we'll just go into 4. And the last one I'll be going into if I have time. The first one I'll be dealing with is optimum bandwidth allocation for transmission. How do you allocate frequency slots to different nodes based on some optimality criteria? And then we'll go into joint encoding of correlated sources under energy and buffer constraints. For example, if all the nodes transmit data that are correlated with respect to each other, how do we go about encoding those data, and then how do we transmit them based on energy and buffer constraints? We'll also talk about joint rate and power control strategies, where each node will jointly adapt its rate and the power at which it transmits. Any node can be a laptop or a cell phone or anything. So a priori, I don't assume anything. A node can be as general as possible, whatever we can imagine. And then we can also talk about CDMA communication, which has some link with physical layer, but I'll be going into this if there is time. But about the top 3 topics are more into MAC and network. And then we'll conclude with some discussion. Okay, general wireless network is this. It has a lot of nodes spread across a wide area. And what I assume is this. Each region takes care of a certain number of nodes. So I cluster a certain number of nodes into one particular cell, very similar to a cellular network, cellular communication. So I assume that the geographical area is split into a lot of cells. These cells may be irregular in shape, but they are disjoint. And all the cells, each of them, they have n nodes. Okay, each cell has n nodes in them, and they are assumed a priori. Okay, each cell has n nodes, and they are assumed a priori. And there are totally n plus 1 cells. And what I propose is this. In every cell, there has to be a centralized node called the master node. Okay? So you see that there is one master node in this cell, another master node in this cell, and third master node in this cell. And there's also a constraint that all the nodes that communicate in this cell will have to do so only with the master node. Okay? This cell cannot directly transmit information to this node cannot directly transmit information to this node. Likewise, this node cannot directly transmit information to this node. If it has to do so, it has to do so through the master node. Is that fine? So that's the constraint in which I'll be working, which is a very logical constraint where this is applicable in a lot of systems. You have a question? The nodes are stationary. The nodes are assumed stationary. Okay?
So the assumption an ordinary node will not be communicating to another ordinary node
within the same? No, I'm going to assume this protocol. Okay, and I'm going to tell you how packets are going to reach from this to this, which will be taken care of in routing. Okay, without loss of generality, if I can solve all the problems that I'm going to give now based on one particular receiving node, they will hold for any arbitrary receiving node. You will see that at the end of the talk.
Am I supposed to think about these guys talking to a base station and somebody
Yes,
far away?
yes. Okay, so you can make that analogy that this centralized master node is a base station. But the beauty is, this node does not continue to remain as a master node forever. Okay? So this is what I do. I split the time into cycles. And each cycle is split up into a setup phase and a transmission phase. In the setup phase, a particular node is chosen as a master node. Okay? A particular node is chosen as a master node. And then in the transmission phase, all the other nodes start communicating with this master node. Is it fine? And in the next cycle, there is again a setup phase, so something else would be chosen as a master node. For example, the location of the blue circle will go to this node. Or maybe something else may be chosen as a master node. Okay, let's not go into the details of how the master nodes are chosen. That could be by any algorithm where a node that has not been a master node for a long time could be given priority to become a master node, or something like that. Or a node that has a lot of energy to do that can be a master node. Or the node that has the least amount of interference in this area can be a master node because it's receiving a lot of information, so you would want it to have least amount of interference at that location, right? So every setup phase chooses a master node, and in the transmission phase all the nodes communicate with that, and the location of the master node changes every cycle. And one more thing, the probability, okay, I went into the first 2 points. The transmission phase nodes, in the transmission phase the nodes communicate with the master node, and then the probability that a node connects to the master node is inversely proportional to the distance. Okay, these are all the foundations on which I'll be resting my talk on. Okay, so for example, let's take this node. The probability that this node connects with this master node for a communication is lesser than what this node can do. Okay, I assume that because it's a very logical decision to not allow this node to transmit when it's very far away from this node because it's going to conserve power. Okay, so nodes closer to the master node will have a higher probability of connection with the master node than the nodes farther away. Is it fine? That's the reason why I'm shifting the master node.
Oh, so you're shifting. This is not like a model for cellular.
This is not the model. This cellular system is just a specific example of this. This is a wider class of system.
But it's not like saying people who are far away from base station are less likely to make it.
No, I'm not talking about cellular communication here in a general wireless network. Cellular communication is just an example where the master node is always fixed at the base station. And every node has a probability of one connection if it wants to, right? So that's a very specific example of this case. Let's make the cellular system more general. Let's assume that every node connects with the centralized node only with a certain probability based on the distances. In the case of cellular systems, the probability is 1. Okay? For any arbitrary node, the probability can be made inversely proportional to the distance. It might remain unconnected also. Pardon me? Okay. Yeah, but Bluetooth has a very fixed thing. It doesn't connect beyond a certain point. Yeah. Each node knows where it is. Okay, and then when the master node is chosen, what it does is it broadcasts its location to all of the nodes. Okay, when this guy is chosen as a master node, what he does is he transmits his own location to all of the nodes. And all of the nodes know their respective locations and they can easily calculate the distance from the master. Okay, and then they know and they toss a coin and then they connect with a certain probability. And the nodes farther away have a very less probability connection than the nodes closer. Okay, and one more slight assumption which you can take care with perturbation of nodes, but I do not assume that no two nodes are at the same distance from the master node. For example, no two nodes are the same distance from the master node. Okay, I assume that. Is it fine? So I'm just going through all the assumptions for the talk. And this is the last slide that I'll be talking about assumptions now. This is a definition. Okay, now what do we have? We have a set of nodes that want to connect with the master node, and each node has a probability of connection. Right? If you rank the probabilities in a set, that would form a chain, that form a monotonically decreasing set, right? The node closest to the master node will have the highest probability, the node farthest from the master node will have the lowest probability. So if I rank all the probabilities in a set, that will form an ordered chain. Okay? Now, and it will be a monotonically decreasing set of values. I call such a cell as a prioritized cell. So each region, each cell that I defined is a prioritized cell. And I call it an alpha prioritized cell because there always exists such an alpha less than 1 such that the lower probability is almost alpha times the previous highest probability, where alpha is less than 1. Can I assume that? Do you agree with me? When probabilities are monotonically decreasing, the k plus 1 probability can be alpha times, at most alpha times the kth probability,
Sure.
where alpha is less than 1. Okay, so let's go. Now, I don't want to go into the routing aspect. Okay, now this is the scenario in which the system is working. This is the protocol. Okay.
But now that alpha is a constant, alpha in internal big notation is not being mentioned.
Pardon me?
Is alpha now going to be something that doesn't need to be mentioned?
The exact value is alpha. The constant need not be known. The value need not be known, but I'll just assume it as alpha.
I didn't say no. I said it's mentioned. You no longer mention it. You write big O. Write big O could be there's power of alpha squared.
Yeah.
Okay.
Yeah. Now, the issue is this. What I'll be doing is, I'll be proposing a few algorithms on this particular class of networks. Okay, one question was raised. How does a node communicate with another arbitrary node in a cell if it has to communicate only with the master node? The reason is the master node keeps on changing its location, and this is the way it does. For example, this guy has to send packets to this guy. When this guy is a master node, what it does is it sends all the packets to this red circle. Okay, and then all the packets have gone from this origin to the red circle. Now, after a certain point of time, this red circle ceases to be the master node, and this blue circle starts to be the master node. Okay? So the packets move from this red circle to this blue circle, so based on certain probability. Is it fine? And the packets keep hopping from the source to destination. This is how the routing goes on. Is it fine? Is it okay?
So you're routing within the same cell.
Routing within the same cell. Okay? Routing within the same cell. For example, if I assume that this is the master node, okay? If this guy wants to communicate certain packets, he's very far away from this node, okay? So he has a very less probability of connection with this master node, okay? So he may not so the probability is very less. So if this guy has to transmit this packet, I should make sure that at some point master nodes also appear in this region, so that he has a higher probability of connection. Did I answer the question? No, center of the net is always fixed because the nodes are stationary.
Oh, no, I'm just saying you assume that new devices come into the network.
Yeah.
So that way
The new devices don't. I assume that the cell has a priori n nodes at any given point of time. Yeah.
I don't understand the protocol. You start
For example, let's assume that this node wants to send packets to this node.
Okay, I got that.
Okay. In a particular cycle, this guy is the master node.
Okay.
Now there is a probability of connection with this node.
Okay.
Okay. So when it connects, it sends all the packets to this node. Okay. Now, that means the packets have already gone from here to here. Now the remaining distance is this, right? Now this guy has all the packets. Now he's waiting for these packets to be dispersed.
Okay.
So he discovers that there is a master node here
Okay.
at some other cycle. So he sends all the packets to this guy.
Okay. So I don't see how you've made choices, right? It seems that there's only one option.
There's only one option, and that option also, for example, if the master node is here, this guy will not transmit the packets here because it's not in the destination, direction of destination. Only if the master node appears in direction of destination, he has that particular choice of sending it across.
So it's the routing protocol. I always look for the master that is closest to being on a direct line and that I can connect to.
Yes.
Okay.
Okay, that's right. Okay, you could show that this is a stationary network, right? As the number of nodes increase, Gupta and Kumar have shown that the maximum you can reach, the rate at which this arbitrary origin can send packets to arbitrary destination, goes over what? Square root of n for a stationary network. That is shown. That's an upper bound. This routing and scheduling protocol achieves that upper bound.
Okay.
Okay. this routing and scheduling protocol actually achieves that upper bound. I'm not going to go into the proof. Okay. Moreover, this is an interesting result. The average hop that each packet will go, right? For example, if this packet has gone from origin to this place, that's a hop. It has traversed this much amount of distance. You can also show that with this protocol, the average distance will be at least this much. It's lower bounded by this expression. Every node has infinite buffer. Delay is unbounded. You can easily see the delay is unbounded, right? The nodes need not be connected at all. It's all based on probability. The nodes may not connect. Is it fine? Very similar to David's model, Berkeley, where he proposed mobility of nodes and delay is arbitrary but still achieves a high rate, data transmission rate. Is it fine? So this is the this is the low bound on the hop length. No, I use a model more similar to David's. Okay. So these are simulations. For example, the lower bound was this theoretical curve, and when I actually simulated the average hop length each packet traverses from a node to a node is this much. Okay. Now let's go into the algorithms. Okay, this is the foundation on which I'll be basing my talk on. That's the protocol model of the wireless network. Okay, there are a lot of protocol models, but I just proposed one, and it has certain characteristics. It achieves a good data rate for stationary networks. It achieves an upper bound proposed by Gupta and Kumar. It also has certain other interesting properties, like it gets a good mean hop length and other such properties. Let's go into algorithms. For people who may not be familiar with what a martingale is, a random process yk is called a martingale. If expected value of yk plus 1, given all the previous values of yk, or in mathematical terms, a Borel function of all the previous yks, is equal to yk almost surely. Okay, this is called a martingale. If such a random process yk exists, that yk would be a martingale. Is it fine? For any yk, this inequality holds. Any martingale yk that satisfies this inequality holds. Okay, if yk minus 1, the norm is less than or equal to ck for arbitrary constant ck, then probability that this expression holds is upper bounded by this right hand side expression. Is it fine? Okay. Now, let me define a new variable called z. Okay. Z is the sum of the indicator function of sets bi. Okay, let me number all the nodes I equal to 1 to n. Is it fine? When I number all the nodes I equal to 1 to n, and the centralized node is a master node, bi is the event that node I communicates with the master node. Is it fine? So the indicator function of bi is 1 if node I establishes a connection with the master node. It's 0 if it doesn't. So sum of the indicator function is going to be the number of nodes that actually desire to connect with the master node. Is it fine? So this sum is nothing but the number of nodes that desire to connect with the master node. If the number of frequency slots that are available in a cell is, say, q, there are only q frequency slots available in a cell, and q plus 1 nodes express a desire to connect with the master node. For example, this variable zn is q plus 1. Then the q plus 1 node is blocked. Is it fine? So any question? Connect with the master node. Okay. No, because that's what I'm trying to say. If the number of frequency slots that are available, for example, if I wish to communicate with some other person, and if I do not have the frequency bandwidth available, then I have to keep quiet, although I decide to connect. Because the node, for example, if there are n, let me go back to this. There are n nodes in the cell, right? Okay, and I assume there is a limited bandwidth. Let's say there are only q slots. Okay, so that means at any given point of time, only q nodes can connect with this master node. There could be q plus 2 nodes that try to connect with the master node, but since the slots are only q, 2 nodes are already blocked. The nodes closest to the master node could be allotted the frequency slots, or the nodes.
But so suppose you queue slots, you 3 plus k people want to use those slots.
Yeah.
How, I'm in those, how do I decide which slots to use?
You will be assigned by the master node.
So, but the map, okay, so, but when does the master node
When you send a bit that I'm interested, say 1 bit, when I'm,
on what slot do I send that in?
oh, that happens in the setup phase, where every node is given a round robin fashion, or a aloha type algorithm, a CSMA CD detect or whatever.
But it could happen that, it could not happen that all of the guys, you 3 plus k people, you all by bad chance, you decide all of people in the same slot. You have to have that, really, just kind of the people who happen to desire to all up
No, what the master node does is, that's a physical layer problem. What the master node does is, it hears from all of the nodes that want to communicate with it. And after it has received all the information, what it does is, it then decides, I'm going to assume frequency slot to this guy. So he sends back information to the respective nodes saying that you will be able to transmit at this frequency bandwidth. Yes.
But the assignment of everybody in the cell
Yeah.
has some
Yes. Yes. You have to assign the slots. But what I'm assuming is there are totally so many number of slots, and these slots, I'm not going to an assignment problem. That's more into physical layer, how the nodes communicate with each other, and then that without loss of generality, I've skipped over it. Okay? We'll talk in a more higher plane when the nodes, if q plus k nodes try to communicate when there are only q slots, k nodes are blocked.
I had a question. On an earlier slide, you said the probability that a node desires to communicate with the master node is inversely proportional to
The distance.
the distance. So that means the expected value of the indicator function of VI is positive, or
The expected, yeah, will be the probability of connection. That's right. So I define this new variable y. Okay. It's a function of this, z, and you can show that this holds for all y at every instant, and also the probability of p, the summation probability of vi, p of vi is less than 1 by 1 minus alpha because it's a geometric series. The first probability is at most 1, the second probability is at most alpha, the third probability is at most alpha square, right? For all the nodes, because we've ranked all the probabilities of connection. Sum of all the probabilities is going to be bounded by 1 minus alpha. So using Asimov inequality, this easily holds. That's an upper bound. The number of, this left hand side is nothing but the number of nodes that desire to connect, right? If it is, the probability that is greater than q will be upper bounded by this expression. That means the probability that nodes are blocked is upper bounded by this expression. If right? Probability that the nodes are blocked is upper bounded by this expression, which is.
I have a question now. That Q in the final expression, up or down or wrong, where does that Q come from? What does it mean?
For example, let's assume that there are QL slots allotted to a cell. We've not done so yet, but assume that we have given QL slots. The probability that these number of nodes will be, that would desire to connect would be greater than that QL would be bounded by this. Okay? We're going to desire QL now, but given a QL, the probability that these many nodes, okay? So that's the upper bound in the blocking probability. So we would want to try to allot slots to the cells that can, based on this blocking probability. The cells that can accommodate a higher level of blocking probability will be given a lower number of frequency slots. Cells that cannot tolerate a high blocking probability will be given higher number of blocking frequency slots. Okay, that's a up bound.
Wait, what's the N there?
N is the number of nodes in the cell. And L is the cell number. QL denotes the cell number. Each cell L has N nodes. And each cell is L is given QL slots. Okay? So you can easily form a utility function based on this. Let's take this utility function. What does this utility function do? If I maximize this utility function, I in fact achieve the problem of proportionally assigning slots. Right? So what happens? I constrain the total number of slots in the whole network to be the sum of the QLs. Okay? I have total Q slots, and I want to assign those few slots to different cells based on proportionally minimizing the blocking probability. This utility function does that. This is nothing but, if I maximize this first term, I in fact minimize the blocking probability, and this term is nothing but a Lagrange multiplier for total number of slots. Is this objective function clear? Yeah.
I have a question about the vector function, which is that by assigning the total number of slots across all the available cells,
Yeah.
there's an implicit assumption that if you use a slot for one cell, you can't use it for another cell. And then,
You cannot, yeah.
yeah,
Later we'll go into the problem of same slots. See, you can easily extend this problem to assigning the same particular slot to two different cells. You could do that
I agree.
without loss of generality. You could say it's an extension of this, simple extension of this. Where,
Something like I have a fixed amount of hardware to allocate each hardware at a master node
Yeah.
handles a certain frequency. Therefore, I don't want to simply over-provision my network by putting all of that hardware in every single place where I can have a master node instead, or what is that?
no. Every node,
Uh-huh.
for example, there are, let's assume, yeah, each master node should be capable of receiving a wide band. And since it's FDMA, you can easily do you can have a frequency division multiplexing receivers are very simple. They can handle a wide range of bandwidth. It's not a problem. If you're talking about CDMA, then that's a difficulty, because if every node would have to, cater to both FDMA and CDMA and everything, then that's a monster node. But in this case, a simple frequency division receiver is simple, right? It can decide whether in which frequency bandwidth you can tune into. It's simple like a radio. Your radio receiver is so simple. It has a wide range of AM and FM. Yeah, for example, yeah, it receives, the master node receives, say, data from 0 to 100 kilohertz. It knows that 0 to 5 kilohertz is from the first node. It also knows that the 5 to 10 kilohertz is from the second node. And it's a very easy filtering problem, right? You can easily segregate the data. Any node can be a master node. Any node can be a master node.
Like in the cellular communication example, you have, like really high channels of consider all these the hex
Right. Right.
that you only care about those interference.
Yes.
So,
But here the interference, yeah.
so here, wouldn't that good property about wireless that, the signal dies down after a certain distance, take care of this? How do you allocate frequency and how do you divide them?
Here there is no interference, because each node has a particular frequency, dedicated frequency slot allocated to that. So there is no question of interference here. No node is causing interference to another node.
So my concern, I think I've been able to boil it down,
Yeah.
is that for the assumption of connectivity, you assume that distance implies something like signal strength weakens, and therefore it's more difficult to connect, and that's why it's just talk to somebody local. Then for the assumption of interference, here, the motivation is then, there will be no interference if nobody talks on the same channel, yet the assumption that connectivity went down would seem to also imply that there was the opportunity for frequency reuse when you go.
Yeah, there's opportunity of frequency reuse. Yes,
Okay,
I agree. I have not gotten into that problem.
Okay.
You're right.
Okay.
There is opportunity of frequency reuse. So this utility function, if I maximize, what I'm trying to do is I'm allocating QL to each L, so that the sum is near Q. Okay, so this is a simple gradient as an algorithm which will achieve that. And it's, right? For example, I'm showing the utility function here. It's concave, nice concave function in the region of interest. This is the region of interest. A nice concave function. And if I'm maximizing this concave function by gradient ascent, it would do it. Alternatively, I can have more constraints on this. For example, consider the same utility function, but I'm adding constraints to it. constraints are that the sum of the frequency slots should be strictly less than q, not near q. It has to be strictly less than q. It's a very hard constraint. Okay? I'm not going to add it as a Lagrange multiplier, but it's a very hard constraint. And let's assume that the buffer size in the master node is say limited. Okay? The number of bits that it can receive is limited. Let's say it's BL. Okay? The cell BL is the buffer size in the master node of cell L. So since it is receiving all the data from all the nodes, its buffer size may be limited. So what's the amount of bits that it receives? It's QL, which is the bandwidth, times the rate at which all the nodes send, which is F, times the time of the transmission phase. So this is the total number of bits that the master node receives. If that buffer size is limited, you can also add that constraint into this by providing, because you don't want to allocate more slots into a cell in which data cannot be transmitted at all. It's going unused, right? So you would want to take care of that assumption also. Is it fine? So you have this concave function and you have this set of constraints. Okay? And this is a plot of the concave function. It's again a nice concave function. This algorithm will achieve that. This is a modified version of the Polyak algorithm. Polyak is a Russian mathematician who proposed solving concave optimization problems on convex or concave sets. And this algorithm, a gradient as a simple gradient as an algorithm will not solve the problem. It will not go to the optimal region. You have to do these kinds of tricks. You have to, because it might oscillate around the equilibrium point. For example, I have a concave function. Okay, I increase it, and I reach near the optimal point, and I increase it beyond. So I go above, and then I keep on oscillating. Understand what I'm saying? Gradient doesn't. Yeah, that's what it does.
This is line search and direction gradient.
In the direction of gradient, but you have to vary these parameters in such a fashion that they actually converge to the optimal point, not go near the optimal point. Gradient descent algorithms can take you near the optimal point, but they will not ensure. There are theoretical proofs that gradient descent algorithms could be oscillating around the optimal point. But we want exact values.
If you're using floating point hardware, then saying I want exact value is kind of, I don't know exactly.
Yeah, if you want to go into the intricacies of, yeah.
But then, a claim for many iterative methods is they quickly achieve the accuracy allowed by hardware.
Yes, this is an iterative approach. All I'm doing is, this is a gradient descent algorithm. If you see, I'm changing the parameter q at k plus 1 as q at k times the gradient, right? Plus alpha times the gradient. What is the modification here? This is a gradient descent algorithm. You're right. But what is the modification that? Alpha k is not a constant. Okay. If alpha k were a constant, it would be a simple gradient descent algorithm. Alpha k has to be such that it has to satisfy these conditions. That's all. Okay, it looks complicated. It looks very complicated, but an example of that is alpha k is 1 over k, beta k is 1 over root k. Right? These two sequences satisfy this condition. Plug in there and put the algorithm, it's going to work. Exactly. That's damping. As you go to the optimal point, you damp. That's right. No, but conjugated gradient is, you need to have a quadratic function. The general objective function need not be quadratic. I know. That's why I'm. No, conjugated gradient, you need to have a quadratic convex function. You cannot optimize an arbitrary objective function using conjugate gradient. So this is how the algorithm converges. Okay.
But you're showing flats now. You had to choose a value for alpha, right?
The alpha, what I did was, when I arbitrarily distributed the network, okay, and when I move the master node around, I'm actually calculated a set of probabilities and then fitted the alpha there. Because since the nodes do not move and they are stationary, Alpha could be found a priori before doing any of
So
these.
what is the alpha about?
It's around 0.95. It's going to be close to 1.
Okay, so what's n?
N is 10,000 hours.
So you're so looking at that expression for Lewis inequality and all that stuff, it looked like you had to have n fairly high and alpha fairly.
That's right. That's right.
Couldn't be too close to
That's
1
right.
in order
That's
for it
right.
to be-
That's right. The bound is strict for high values of n. It's very conservative for low values of n. That's right. And this is an expression for average power consumption. For example, you may not need to know this, but if each channel between the node and the master node, it's digression from the talk. Each channel, this is a channel between the node and the master node. Then the average power that it consumes, based on this probability connection, average power that it consumes is this expression. Yeah. During the transmission phase. Yeah. It might. I have not looked into it. It might. Here are two more results. Again, I won't go into the proof, but they are nevertheless interesting. To have a maximum blocking probability of 1 over mu in any cell, okay, let's assume that the cell cannot tolerate more than a blocking probability of 1 over mu. Then if I allot Q to be this, I would guarantee that, based on this probability of connection. Is that fine? Just for thought to munch on. I'm not going to give the proof. Likewise, if n is very, very large, if n goes to infinity in any cell, okay, intuition says that the farthest node is never going to connect with the master node, right? It always says that there will be an upper bound on the number of nodes that connect to the master node. So when n is arbitrarily large, then the number of nodes that express a desire to connect with the master node will be upper bounded by this. Why is that? Because let's say n is say 100,000. The probability that the 100,000th node connects to the master node is bounded by alpha power 100,000, right? But then I'm showing you a strict bound. Min.
It's not dominated by n. It is dominated by the square root.
Yeah. Dominated by square root. It also depends on alpha. Yeah.
It is still
Yeah. These are interesting results to munch on. But intuitively I gave the idea, but proof is slightly involved. So, like for example, if I can tolerate a blocking probability of 0.2 for 30,000 nodes, I want a blocking probability of 0.2 for 30,000 nodes, then it's enough if I have 350 slots.
Once you assume a certain alpha.
Yes, the alpha is 0.95 for this simulation proof. Is it fine? That depends on alpha. That's what I told you before.
Yes, I just find that to say I can support 30,000 nodes with 350 slots, there's a big caveat there. The caveat
That's because
they're going to be further and further away, so they're not even going to try and connect.
Yeah, that's the intuition behind it.
Okay.
But then when someone comes to you, give me the expression for how many slots should I use, the number of nodes increase. That's an expression.
So I guess alpha kind of tells 0.95 means the probability is rolling off pretty quickly.
Right.
Which means things are pretty far away, right?
Right. We are now going to the second algorithm. Let's do joint encoding of data. We are assuming that all nodes are there, transmitting a centralized master node, right? To alleviate the problem of Gupta and Kumar discovered, you might alleviate the problem by doing encoding of data. Let's assume that the data that has been transmitted by all these nodes is jointly correlated with the Gaussian distribution. Okay, let's assume that all this data is transmitted with Gaussian distribution. Now I'm going to encode and then send it back. to this. Encode and send it back to the master node, and master node is going to decode. And with a certain distortion for each node. Okay, let's assume that di is the distortion level attained for every node, I. What should be the rates R, I, that I should send? Distortion is nothing, whenever you encode a data, you decode it back. You won't be able to get the same data again. For example, if I send X here, and I encode it, and I get decoded again, I get another variable X hat. Okay, the difference, mean square distance between X hat and X is called the distortion.
Encoding is like error correction,
Encoding, you can do any kind of encoding, it's just arbitrary. Encoding could be anything. Decoding, you have to appropriately decode based on the encoding procedure that you use. Assuming that this function, you have to figure this out, what this function is. Okay, I want to attain a distortion level di for every node. That means there will exist an encoding procedure if I send the data at this particular rate R. Is that fine? There will always exist an encoding procedure. If I send that particular rate R, there will always be an encoding procedure that will achieve the distortion level D. What encoding procedure, that you have to discover. Okay, but superficially there exists an encoding procedure and there exists a decoding procedure. And we want to get data at a certain distortion here. So that's the definition of distortion, right? The distance between X and X hat. That's the distortion. That I want to be less than di for every node I. Okay, and these are encoding functions. And I want to figure out the rate at which they send. This is a rate distortion problem. Very, very familiar rate distortion problem. And a lot of people are working on this. So what I am proposing is an outer region which is very close to, which can achieve a close enough distortion level that you desire. This is a rate distortion region for me. Every node I has to transmit at this rate. Okay, I won't go into the proof of this. It's a simple procedure. And on top of that, I put buffer constraints and energy constraints of every node. For example, if every node has a maximum energy EI that it can transmit at, so let's assume Ri is the rate at which it sends. E bar is the average joules per bit that it will transmit. P bar is the transmission time. So this left-hand side quantity is nothing but the total energy bit spent by the node, right? That's the total energy spent by the node. If that is bounded by E, and let's assume the buffer size. This is the total number of bits that's received by the master node. And let's say it's bounded by B. And we have included the rate distortion region here. And this is a utility function. What this utility function does is, it maximizes the amount of data that you send. The lesser the R, the more the data you send. The stronger your encoding is, the more data you send. So you maximize this utility function based on this region. Is the problem sitting clear? This is the rate in bits per transmission, right? Ri has units bits per transmission. And let T bar be the transmission, number of transmissions. Transmission times bits per transmission is going to be the number of bits received from one node. Right? Is it fine? You do it for all nodes, you sum it for all nodes, you get the total buffer capacity. Likewise energy, and likewise this thing. And this is the covariance matrix of the correlation. One guy is a must node. The lambda will change. But on an average, if you assume in data collection environment, you're not going to send intelligent data. Suppose you're just going to gather data. In that sense, you can assume this kind of a model. So,
isn't that lambda I actually a general in that even if they're perfectly decorrelated, that's just a certain set of values for lambda I?
That's totally decorrelated. Yeah, all these things will be zero. Optimizing variables will be zero.
Okay.
It's going to be a diagonal matrix.
Okay.
And then you're not going to achieve any rate, encoding rate. You're going to get a good encoding rate only if they're correlated. Okay. If two nodes are not correlated, there's no point encoding the data together. This one is an algorithm that will again achieve the distortion region. So this is again the modified version of the Polyak algorithm. Okay, very similar to that. Can I proceed? Do you want to? Okay. Okay, that's the second algorithm. So we've given two collaborative algorithms that nodes can use, right? Let's go into more into data transmission, actual data transmission during the transmission phase. Now let's look at the problem of shared bandwidth in different cells. Let's assume that this cell shares bandwidth with this cell, the point that you raised, right? And now nodes are transmitting. Yeah. Right.
So the node will now know what rate to send at.
Yes. Yes. Compress and send.
And is there any other communication that's required between the nodes?
No. No.
So like you prime, that's just a function.
That's it. That's a distributed algorithm.
So how are we going to know the constraint?
Oh, the constraint. Yeah, the master node has to set back the constraints. The master node has to do this buffer. Certain constraints have to be centralized. But as far as the rate goes, it's not centralized. If you go here, these constraints need to be centralized because they take care of other nodes also. But these two, if you remove these, this will be strictly distributed. You can include any number of constraints that one might think of in terms of other parameters. The master node will take care of that if it's centralized. But then, yeah, as I told you, you can include as many constraints as possible based on the realistic scenario that you're looking at. The particular encoding procedure will depend on, you will have to decide what the encoding procedure is. And depending on what the encoding procedure you do, that's not going to achieve the distortion level accurately because information theoretic derivations are normally for n tending to infinity. So, but then you have to also make sure that whatever encoding procedure that you do, you have to come close to the distortion level as possible, right? So when the nodes use shared bandwidth and they want to send data, how do they, then there is interference. Let's say we now have to jointly control the rate and the power at which they send. How do we do that? Let's assume this is the master node, this is the master node, this is the master node. All the nodes are transmitting here. I is transmitting to its master node. Okay. Now what is the signal to interference ratio for this I? It is this, right? It's its own transmission power divided by all of the interferences that cause interference to this guy. Is it fine? For example, if J also transmits the same bandwidth, L also transmits the same bandwidth. Now the interference for I is going to be sum of these two powers. So signal to interference ratio is going to be Pi times the channel gain divided by all of the powers that use the same bandwidth, right? Now the issue is this. The node I has to take care of the power at which it transmits based on the signal to interference ratio present at this master node. It has to increase its power if the SIR is very low. It has to decrease its power if the SIR is very high. Likewise, the rate at which it transmits will also depend on the SIR because by Shannon's formula, the rate at which any node will send will directly be proportional to the SIR present at the receiving node, right? So there is an interrelationship between the rate at which a node sends and the power at which it sends. These two are not disjoint. I cannot send, say, 100 Mbps. I may not be able to send 100 Mbps data rate at, say, 0.1 milliwatts when the interference is maybe a lot. And I don't have an encoding and decoding procedure to do that. So I need to jointly control the rate and the power at which I send. Let's put a TCP kind of algorithm here. This is the rate at which each node updates its This is an algorithm. Each node updates its rate. For example, rate at which it sends at k plus 1th instant is the rate at which it sends at kth instant times an additive term. If there is no congestion, okay, this will keep on be increasing the rate at which it sends. If there is congestion, it will reduce the rate. Do you see there is a multiplicative decrease and there is an additive increase? This is a very known TCP algorithm. I have borrowed this from TCP literature for wireless networks. Okay, this is the rate at which it sends. Now then I have to cater to the, if this is the rate at which this guy is going to send, it also has to adapt its power level appropriately so that any encoding and decoding procedure will achieve arbitrary low bit error rate. How do I jointly update this F and P? Okay, I won't be going into the derivation. I'll just, this is the derivation, I'll skip the derivation because okay, this is the way in which I do. Pardon me?
SIR has to be with respect to the base station.
Yes.
Master.
Yes.
But this rate control will be done on the sender.
Rate control is going to be in the center.
So, will the base station tell the sender that this will be SIR and C?
Yes, it will give a noisy measurement of SIR. Even your cell phone receives a noisy measurement of SIR. Sometimes it's called a CLPC. Instead of sending a noisy measurement of SIR, what they do in closed loop power control is this. The base station sends a couple of bits requesting the node to increase or decrease its power. But in our case, we are going to send a noisy measurement of SIR. Okay, it's possible in data networks. Sending an 8-bit data is not going to be a problem. So this is the rate at which I update, this is the algorithm at which I update my rate. The rate at which at k plus 1th instant is the rate at kth instant plus this term, which is the traditional TCP algorithm, plus an additional control term that I plugged in. This control term will be this fashion. Okay. Power. See, UK is a vector. UK is nothing but UP and UF put together. Okay. UP is the power control term that I added to the power update equation. This is the power at which the node has to transmit at. Okay. The bottom line is the rate at which the node will send. It will do these two things simultaneously. If it does these two things simultaneously, then I can ensure that there will be an encoding and decoding procedure that will give you an arbitrary low bit error rate, because I'm making sure that the SIR present in the receiver is going to be what I need. Yeah.
So the discussion of rate control wasn't just the nodes using TCP, it's that you're going to have an update strategy that
On top of TCP.
on top,
This alone is TCP.
I wouldn't really say it's on top.
Because this additive control is on top of TCP.
I'd say that changes.
It changes. Yeah. It changes. But then the backbone is the
So the next question I have about
Yeah.
that is, if you take in the actually plus 1,
Yeah.
those matrices there, I don't see where they have zeros, where they have non-zeros. Does it require each node to have global? What does it require
Oh,
each
I
node to
didn't
have
tell you
global?
what it is A, B, and C are. If you write it as a state space model, okay, both the rate and the power, if you club it into a single state space model, you can write it as a state space expression. Simple state space expression where this, UK as I told you is UP-UF. This is the actual and the desired SIR in the master node, right? For example, let me be clear. If I need to send, let's assume you are the master node. If I need to send data to you, I'm sending it at rate F. Now I should make sure that based on this F, you need to have a particular desired SIR present at your level. But am I transmitting at that power so that the actual SIR that is present is same as the desired SIR? I may not. So let's assume that the actual SIR is gamma and the desired SIR is gamma prime. This desired SIR is got from that rate at which I send. This is what I need to have at your place. But based on the power level at which I transmit, this is what you actually have. Okay? So you can simply write the state space, you can derive the state space model for this. Okay, where xk is this vector, xk plus 1 would be given by this iteration every instant of time, because my rate is given by an iteration, right? If my rate is given by an iteration, the desired SAR is also given by an iteration. Is it fine? Because the desired SAR and rate are proportional to each other. So if my rate is given by an iteration, my desired SAR is also given by an iteration. Likewise, if my power is given by an iteration, the actual SAR is also given by an iteration. So I can combine those two and write them as an iteration, which is that matrix. This matrix is A, B is identity.
No, I still don't understand what the master node needs to have knowledge of in order to have that matrix A with which to complete the
This is entirely distributed. What the master node does is this. It just sends a feedback of the SIR to every individual node. And at every node, this takes place. Do you agree that the SIR will, see, for example, let's say there's interference present at 0 to 100 kilohertz. That's what I'm transmitting at. Some other node is transmitting from 100 kilohertz to 200 kilohertz. Okay, I'm not interested in that interference. I'm transmitting to you at 0 to 100 kilohertz. Now you give me a interference feedback saying that you are transmitting a 0 to 100 kilohertz and this is the interference that I have. And you will also send a feedback to him saying that you are transmitting at 100 to 200 kilohertz. This is the interference you have.
So is there any interference between these nodes?
No.
Sending feedback to?
No.
Coming from other cells.
Some other source.
From other
So
cells,
there's some other
neighboring
factors
cells.
that are not affected.
Within your cell you get DMA. Your interference comes from the other cells.
And there's an assumption that there's no feedback there to the other cell.
No feedback to the other cell.
And not just no feedback explicitly, but no feedback implicitly in being able to write these models out.
No feedback implicitly also. Only there is no feedback whatsoever going between one cell to another cell. Though the interference,
I think I understand.
though the interference comes from the other cells, the algorithm is entirely distributed in which every node in a cell will do this update. The rate at which it updates data is this expression. The rate at which it updates its power is this expression. What is the objective function? That's what I'm trying to do. The objective function is nothing but the norm square between the actual and the desired SIR. X is the actual and the desired, right? L is the vector 1 minus 1. So Lxk is the difference between actual and desired SIR. So if I minimize Lxk, I'm in fact minimizing the difference between actual and desired SIR. Use the control, amount of control that I give. I want low control. I don't want to, destroy this TCP algorithm. All right? So in the sense, this distributed algorithm will in fact make sure that you have an actual SIR that is close to the desired SIR, whatever you would like to have, and in that sense you will guarantee that there exists an encoding procedure so that you will get a bit array, good bit array. Is it fine?
Was it possible? Would it have been impossible to have simply the TCP update strategy in the bottom line and some different update strategy in the power line? Or was that?
Yeah, it is possible. I have derived the results for based on TCP. It is possible for you to give. There are a couple of papers in the literature that propose another kind of rate update. It's more to do with it's going entirely away from TCP. Okay. To give you an example, this fk plus 1. What they do is alpha times fk. It's that simple. What they do is every iteration they change this alpha. Okay, there the control is coming in terms of finding the alpha. But then I don't want to go far away from TCP because TCP is ubiquitous, and you want natural extension would be to take it to wireless networks because it works. You know that it works.
Right. I guess I was just curious. Is there a fundamental reason for the TCP update strategy to not be something that you can just take as is and entirely make some modifications in your power update?
You can. In that case, what would you do? you would put that UF as 0, right?
And
Be-
still will converge.
You still, but the performance won't be that good.
What do you mean by that?
I'll explain.
Okay.
I'll skip all these. Okay, let's assume. We want the error variance between the actual and the desired SAR to be as close as possible, right?
Okay.
Let me explain. If I make that UF as 0 and keep that as TCP algorithm, and then do the power control alone, the difference between the actual and the desired SAR may be somewhere here. Okay, I don't have that plot,
Okay.
but it will be somewhere here. But if I add the rate control also, then it will go down by a dB. You understand what I'm saying? And the top in these plots, here the simulation parameters are considered 9 cells. Now you consider 8 nodes in each cell. And if I use a very crude algorithm, no joint rate and power control. Rate I do it as I want, and power I just use a crude procedure based on SAR measurement. I get this. This is a traditional algorithm which is being used. There's no joint rate and power control in TCP kind of algorithm. So that's this is the algorithm proposed by Foschini and Muljanik. It appeared in Transactions on Vehicular Technology. They are in Bell Labs. But they did not even solve this kind of problem. Their problem was something else. But that kind of power control will give this kind of error variance. If you incorporate the control strategies, you get something like this.
Traffic in airlines in the whole cell?
Traffic in airlines, that's a nice, traffic in airlines is nothing but, see, the nodes come in and go out. What I assume is the nodes would like to transmit and not transmit, right? So I'm digressing from the fact that they connect a priori, they connect with the probability. What I assume now is a queuing kind of model. Nodes would like to transmit at a particular rate, say arrival rate. So I constitute that as an arrival rate.
So then, traffic airlines,
Traffic is nothing but the arrival rate of nodes divided by the departure rate of nodes. When nodes start transmitting, I assume that they have arrived. When nodes stop transmitting, I assume that they have departed from the cell. Okay?
because if you use airlines, it's a very small number, 4 to
No. Airline is simply the ratio, it's not a small point. It's a ratio between the arrival rate and the departure rate.
I was actually just going to ask that. I'm not familiar with the unit for.
Go ahead. Oh, okay. And if time permits, I'll go into this. Otherwise, I'll stop here because this has to do something slightly physical layer.
Well, it's been an hour.
Yeah.
How
For example, here we never talked about how the node is going to receive, the master node is going to receive. If it's FDMA, it has a simple receiver structure, right? It uses FDMA slot, frequency division multiplication receiver. That's simple. But if each node is communicating with CDMA, okay, how do you handle a receiver when it has multiple paths? Because these are wireless. Let's assume that this guy wants to communicate with this guy, and it has multi-path channels because of reflections from mountains, houses, everything. Okay?
maybe it's appropriate to discuss
Yeah,
this in terms
yeah,
of,
physical layer.
other work or
Yeah,
future work
yeah,
or something.
yeah.
Rather than open it.
Yeah. So in that sense, what I propose is a receiver structure here for all the nodes that are communicating. So it has to have a receiver structure here, right? So how do I design a receiver structure that will guarantee a low bit error rate from all these nodes if they have multipath? So that receiver structure, it's this. It's what is happening. Every node communicates with centralized base station or whatever you call through multiple channels, multiple paths. And this is the receiver structure. This is the signal processing point. The filter of the signal processing contribution. Everything else is borrowed from the physical layer of communication systems, digital communications. Okay, this will guarantee a low bit error rate. I'm not going into the details of that. So, question?
I have a question. That's a question.
Yeah.
Can you contrast the work you did on the model for frequency allocation with previous models for frequency allocation?
In the literature?
Yeah, in the literature.
No, I haven't found any previous work as far as allocating slots are concerned.
Okay.
We can take this time to
Yeah.
the algorithms that you propose your clustering framework.
Yeah.
If I replace it by the following, I say you have different cells, and there's one node which is mobile, but it is doing a random mode within that cell.
Right.
Would the performance be roughly similar?
In terms of what?
I mean, overall,
Talk?
throughput you can get here.
No, as far as throughput is concerned,
Yeah. Because I mean, essentially what you're doing.
it would be, obviously it would be better than 1 over square root of n.
What I'm saying, the essential probability is right? You're having the master node
Right.
randomly move.
Exactly. This is what happens in David Say's paper also. David Say, that's the analogy between this and that. There, the nodes themselves move to the destination. Here, the nodes move in terms of the location of master node. So since both are random, but then this would definitely achieve better than 1 over square root of n, but I don't know what the exact figure is, but it does achieve square root of 1 over n, that you can show. But if the nodes are mobile on top of the master nodes moving its location, then definitely you can study what its rate would be. That would be a very interesting problem.
Your model is basically that you have one cell with
Yeah,
one master node that keeps
yeah,
a number of ordinary nodes,
yeah,
and then you have multiple cells.
yeah.
And the master nodes are the ones that enable communication across cells. Or is there no communication?
I think master nodes will enable communication, intercellular communication.
So then the question is, some of the graphs that you just passed by for performance for 10,000 nodes and all,
Yeah.
how realistic is that assumption given this particular model that you have multiple cells? Because
In the simulation, I have not tried to transmit information across cells.
well, irrespective of across cells, so here the earlier graph here that you said that you need 3 minutes to plot
Yes, that's,
10,000 nodes, 20,000 nodes.
yes.
something you're talking
No, what the plot I showed was theoretical plot.
Right. Even theoretical, that's fine.
Yeah.
What I'm asking is, from a realistic point of view, is it feasible to assume that we can have 10,000 cells? 10,000
Oh, it is possible. It is possible.
In what sort of a scenario?
The first thing that comes to your mind is sensor networks, where you distribute everything in Africa and you across in the atmosphere, or even bioterrorism. You distribute all the nodes and you want to gauge the amount of toxic content in the atmosphere. You're talking about millions of nodes.
So in that case, then, typically you've done joint power optimization
Yeah.
and joint data power optimization. We are assuming that you have geographic knowledge and everything. So won't that impose a considerable overhead in that the advantages that you gain from your specific algorithm?
Yeah.
Do you think that they might be offset by the overhead involved in coordination and media erection and everything?
Yeah, that's a good question. When n is large, yeah, there will be an overhead. But then if we can try to allocate dedicated, say, CDMA channels or something else, or dedicated frequency slots, the control signals that are going back and forth, then they can all take this simultaneously. But then I'm only interested, so that can happen in the setup phase. All the control signals that go back and forth will happen in the setup phase, and when actual transmission happens, which is much larger than the setup time, in that case, you use this bandwidth allocation.
So when you say that you use dedicated channels for
Yeah.
then that will automatically lead to a throughput increase, right? So you have 100 kilobits in the diameter one of the channels. That's for the right? So
1 or 2 channels separate from these.